Alright, pre-calc students, welcome to lesson 7.4 on modeling with exponential, log, and logistic functions. I'll try to get through this one a little quicker than I did on the last one. Okay, and so what we've got just to begin is the different kinds of functions that we've seen in this unit in particular. There are two to kind of bring your attention to. The one is the Gaussian model, and in particular, those of you familiar with the bell curve, this is one of the ways to produce that bell curve. Our Gaussian model, not hugely important for us for this particular unit, but it is an example of a graph that is exponential and has got asymptotic behavior, and so that's one of the reasons we include it here. The second one that we're really going to focus on is this idea of a logistic growth model. Okay, and so I'll talk a little more about those as and when we need to. So example one is asking that we identify the asymptotes for each of the above functions, and I'm gonna draw those in as dotted lines and write the equation. Okay, and so we start off with our exponential growth model, and so what we should know is that e, of course, has a numerical value which is larger than 1, and so we have an exponential growth function, and it's horizontal has a horizontal asymptote at y equals, or f of x equals 0. Then in the second one we have got exponential decay, so e to the power of minus r, or 1 over e to the power of r, and so now we're going to have exponential decay in this particular case, and once again we have got our horizontal asymptote at y equals 0. Similarly, for our Gaussian model, this is often used to model the normal distribution, and the theoretical underpinning of the normal distribution, of course, is that there's an infinite number of numbers or objects that you are attempting to show the distribution of values for. Okay, and so horizontal asymptote at y equals 0, and then we move to our logarithmic models, and so in both cases, for natural logarithms and for common logarithms, of course natural logarithm is base e and our common logarithm is base 10, and in both of those instances we have got a vertical asymptote at x equals 0, and that of course is because logarithmic functions are inverses of our exponentials. And then the new function that we're going to deal with today is called a logistic growth model, and so the idea here, so let me answer the question first and foremost. We have got horizontal asymptotes, and in this case, based on our graph, we're going to have a horizontal asymptote. In this case, it's showing as if it were 3, but effectively what we're looking at is what is happening to the function. And so if I focus really on this general function over here, what is happening to this function as x approaches infinity, and so what is the limiting value as x approaches infinity, and what that is going to cause is, of course, for this term over here to approach 0, and our asymptote therefore will approach y equals the ratio of a over b, and for the second horizontal asymptote is simply going to be at y equals 0, which is of course going to happen as x approaches minus infinity. So again, in the context of the specific graph that you've been given, you can see the ratio of those two terms produces our horizontal asymptote at 3, and then of course as x approaches minus infinity, this term over here will approach infinity, and therefore we will approach a 0 from above for the value of the function. Okay, so let's move on to example number 2. So now we're looking to find the domain of the function. Our function in this case is logarithmic, base E logarithm. And so essentially what we're looking for, so we know that we're dealing with a function that has the approximate shape of the graph that I've just highlighted. And so what we need to do is ascertain, first of all, where our vertical asymptote is, and then we just need to figure out whether we are moving to the right or to the left of it, because of course we must consider whether or not there's been a reflection over the y-axis. And so if there had been a reflection over the y-axis change in x, then of course instead of having this kind of function, we would be dealing with that kind of function. And so in this case that isn't the case, but that's of course something that you want to pay attention to. So in this case really what we have to focus on is the fact that you cannot have a logarithm with a negative numerical value, because of course it's e to the power of what will produce a negative value, and there's no such value. And so essentially what we need to do is solve the inequality 2x plus 5 greater than 0, and that will give us our domain. And so in this case x greater than minus 5 over 2 is our domain. We have a vertical asymptote at minus 5 over 2, and our domain is x greater than minus 5 over 2. Okay, for example number 3, we have been asked to find the equation of the function in the form f of x equals a times b to the power of x. So essentially we're after two things. We're trying to solve for two variables essentially, which is why you've been given 2 points. It's essentially a system of equations. And so we have the point when x equals 2, the function value is 1.12. So 1.12 is equal to a times b to the power of x, which in this case is ab squared. The second one, when x is equal to 5, here is our function value, and so we have 0.07168 equals a times b to the power of 5. And so in this case, what I'm going to do to begin with is I already know that a cannot be 0 and neither can b, and so I don't have to worry about dividing by a variable. I'm going to take my second equation and divide it by the first equation, and so 0.07168 divided by 1.12, because that's going to then allow me to have ab to the 5th over ab squared. The a's will cancel, and I'm left with b cubed, and if you cube root both sides of that equation, we're going to end up with b is equal to 0.4, or of course in fraction form 2/5. What remains to be done now is of course for us to then solve for a, and to do so we'll just substitute back into our equation. So 1.12 is equal to a times 2/5 squared, and so once we do a little bit of rearranging, you will get your a value, which in this case works out as 7. Okay, and so to answer the final question, f of x is equal to 7 multiplied by 2/5 or 0.4 to the power of x. Okay, quick little aside here, and so we could also take the function a times b to the power of x and write it pretty much in the form of the PERT formula, what you need to see here is that where we have f of x is equal to 7 times, and this time I'll write it as 0.4 to the power of x, our f of t function is p e to the power of rt. And so the two things you need to see here are, first of all, that the x has essentially been replaced by the t, because f of x and f of t, and so essentially all we're really trying to do is equate e to the power of r to 0.4. E to the power of r is going to be our growth or decay factor, and so if we were to simply solve e to the power of 4 equals 0.4, which of course I'll do by taking ln of both sides, or introducing a base e logarithm, and then moving the r to the front, I will have r equal to ln of 0.4, and this allows me to rewrite the equation as f of t equal to 7 e to the power of t multiplied by ln 0.4, and we've now converted the equation to the PERT form. Okay, example number 4, and so what I'm going to do in example number 4 is I'm just going to focus on the initial setup that you're going to need, and just talk you through what your steps should be, and then I'm going to do a complete working of example 5. They're essentially the same idea, and so in the interest of time, I just want to focus on the main conceptual ideas. Okay, so we have radioactive isotopes decaying exponentially, and really the most important phrase here is that we have a half-life of 1,599 years, and so like anything that's naturally occurring, the decay or the growth is going to be continuous. There's no compounding factor, and so we're using the PERT formula, and as you can see over here, it's given, and so what the key here is for you to recognize that half-life essentially means whatever our initial amount that we had after 1,599 years, we have got half as much as we started with, e to the power of r times, in this case, t, 1599. And if you divide both sides by p, again, p is a variable, but you can divide by the variable in this case because we know that p cannot be 0. In the context of the problem, if you had 0 initially, there is no decay, you don't have any of the substance. And so when I divide through both sides by p, of course, those are going to cancel. And the point of showing you this was really, we could have gone directly to this step over here, 1599 times r. And what we're doing in the first instance, this information here, the half-life, allows us to solve for the r value, and we will then be able to answer the second part of the question, which then asks us to solve for a specific given initial amount with a specific number of years. Okay, so very similar in number 5. The main idea that I wanted to focus on in that is for you to understand that the half-life essentially involves equating to 1/2, e to the power of rt equal to 1/2 for a half-life equation. Okay, let's move to example 5. And so, excuse me, we are once again using our PERT formula. Again, you have got two variables here. We're interested in knowing what the initial number of fruit flies is, and we're also interested in knowing what our R value or percentage growth per period of time is going to be, and our period of time in this case is days. Okay, so I'm going to do my initial setup of my equations. I know that there are 100 fruit flies after 2 days, and so 100 is equal to p e to the power of 2r, and so 2 being time. My second equation, 300, is equal to p e to the power of 3r, and that's going to be after 3 days. If I divide those two equations by each other, and so I'm going to divide the second equation by the first equation, I will get 3 is equal to e to the power of r, and so that is going to be my growth rate, and specifically if I want to solve for r, therefore r is going to be ln of 3, so I would introduce a base e logarithm to both sides and rearrange to solve for r. The second thing I'm going to need is to find, so I've now solved for r. The second thing I'm going to need is to solve for the initial number of fruit flies, and I'll need that information to then answer the last piece. So I'm going to substitute that back. Actually, it doesn't matter which of the two, and so 100 is equal to p e to the power of 2 ln 3, and so now I'm going to solve for p. a little bit of a rearrangement in the exponent here. So this, of course, if it appears on the calculator paper, could be very easily and efficiently done on the calculator. As it turns out, this can be really quickly and easily done algebraically as well. And so I'll just show you the steps. PELN to the 3 squared. And then we're going to do two things. First of all, use the property that says E and ln are reverse operations. And so that's going to leave me with 100 equals 9p, and the 9 came from 3 squared. And therefore P is equal to 100 over 9. Remember, this is a mathematical model, and so 100 over 9 gives us 11 and 1/9 of a fruit fly. We recognize that that's not a possibility, but that is one of our flaws of any mathematical model, is that it's going to have those kinds of limitations. And so we're just going to not truncate, not round. We'll just take the value as an exact value. Okay. And then the last step, of course, would be to actually answer the question, how many fruit flies will there be after 5 days? And so we're now saying A of 5. So A of 5, the amount after 5 days is 100 over 9 multiplied by e to the power of 5 for number of days multiplied by ln 3. And with a little bit of algebra and manipulation, or a calculator, you're going to find that our answer is going to end up being 2,700, which is an exact number and is realistic, but either way we would not truncate. We would just give the answer to at least 3 decimal places, and then of course remember to include our units. Okay, so lastly what we want to look at is this idea of a logistic model, and what a logistic model is trying to take into account essentially is that you have this kind of exponential growth, like obviously the example that is timely now is the spread of the COVID-19 virus. You're going to have these what appear to be pretty close to exponential growth rates, but particularly in places where you've got a limited population, or if you think of bacteria growing in a petri dish, there's only so many that can grow, and so you have this leveling off effect that starts to happen, and that's why a logistic model is really a good model to describe things like the spread of disease, where we have a limited population size, for instance. Okay, and so the functions. Well, let's just go straight in and look at example 6. And again, what I've got is a couple of the sections where I'm just going to really talk you through the initial setup. And so I'll just read through this quickly. On the SAS campus, we've got approximately 4,500 people. Student returns from interim with a contagious virus. This is our function that models the spread within the SAS community. And then we've got a parameter here that SAS is going to cancel classes when 40% or more of the people on campus are affected. Okay, and so this is going to be a function of time, and the unit of time that we're interested in is days. And so first things first, find f of 5. And so what we're going to do there, of course, is substitute 5 in the place of t, work out the numerical value. And so that's going to be something you'll do on your calculator. Again, in the interest of time, I'm going to just go straight to the answer. And so that's going to give you approximately 53.956. And so that is going to be 53.956 infected people. Remembering two things, don't truncate. We just want to leave our answer correct according to the required number for rounding. And we want to remember our unit. And what this effectively means is it is what the model is predicting that our infection rate will be after 5 days. And so that is going to be the number of people infected after 5 days. Okay. I do really want to, well, actually, I'll talk about that in the next part. And so Again, let me just come back to part A. That's the number of people infected after 5 days according to the model, recognizing that our model is going to have some limitations and flaws. Okay, let's talk for part B about any horizontal asymptotes. And so what we need to consider for horizontal asymptotes, remember horizontal asymptotes have to do with end behavior, which means we are attempting to determine if the function has got a limiting value, if it tends towards a specific numerical value as x tends towards plus and minus infinity. And so what is happening to the function as x tends towards plus or minus infinity. And so if you imagine substituting in very large t values, so actually in the context of this, of course, it's not x, but t. And so as time increases indefinitely, will we approach a limiting value according to our model. And so if I was to substitute in very, very large positive t values, it's e to the power of minus 0.8, which means that, of course, goes to the denominator. And so let me just show you your function in another form is 4500 over 1 plus 4499 over e to the power of 0.8 t. So I've accounted for the negative, and I want to do that just so that you realize as I substitute infinitely large t values, this numerical value will get infinitely large, which means this term will get infinitely close to the numerical value of 0. And so as t approaches infinity, f of t will approach the numerical value 4500 over 1. So the ratio of those two numbers over there. And so we can conclude that we have got a horizontal asymptote at y equals 4500. And then the second one is mathematically what's going to happen. And so as t approaches minus infinity, we're going to have f of t approaching 0. But what you need to consider in the context of this model is that we cannot effectively model what happened prior to the time when we were first made aware of the infection. And so it's not relevant or realistic for us to be able to backplot the infection. First of all, we don't have any knowledge about this time, and this indicates the first time we discovered anybody being infected. And so in the context of these problems, this horizontal asymptote is not relevant to our model. Okay, and last but not least, again, I'm just going to focus on the initial setup, and then I'll help you with the answer here. And so part C is asking how many days, after how many days will SAS cancel classes? Of course, according to the model. And so all of our calculations are based on the given model. And so that's where we're going to use this information over here, that the school will cancel classes when 40% or more of people are infected. And so what we're looking for is where the value of the function f of t is equal to 0.4 multiplied by 4500. That is when 40% of the SAS campus is infected. If we equate that to our function, and solve for t, which of course we could do algebraically, but would be more efficient to do graphically. And so I'm just going to do an approximate sketch. And so we're not interested in the portion where before time started as far as we're concerned. And so you're going to have your f of t function over there. We're going to have our numerical value of 1800. And so that produces a value of 1800. I'll sketch that on the graph. And so this is our 1800 students, and what we're interested in is the t value for the point of intersection, and for that we are going to get 10.008 days. Don't forget your unit, and don't forget to round to 3 decimal places at least.